Welcome to Math TV with Professor V. In this video, we're going to work on solving a bunch of optimization problems for Calculus 1 students. If you haven't watched my introductory lecture on optimization, I'll link it here. Just click in the top right corner. But I'm just going to do a quick recap in this video and then solve through a bunch of examples per the request of my students who said, we need more examples. So here we go. Just a quick recap about the strategy. So the first thing is you want to identify the quantity that you're trying to optimize. So optimize means either find a maximum or a minimum, okay? Look out for words like smallest, largest, most, least, Then once you figure out what you're trying to optimize, whether it's volume, area, time, etc., right? There's different quantities. You need to express that quantity as a function of one variable. Okay, because you are in Calculus 1, so we only work with functions of one variable. We'll talk about how to do that right now. And then the third thing is then you find the derivative. I'll just say f prime, assuming we're finding f of x, but you could call it whatever you want. Find f prime of x, critical values, and then the last thing, don't forget to do this, verify that your critical value yields the max or min desired, okay? And this can be done a couple ways. All right, so let's just jump into some examples now. I don't number as I go, okay? If you want to number step 1, 2, 3, 4, cool, but I like to just kind of feel it, okay? Here we go. From a thin piece of cardboard, 50 inches by 50 inches, square corners are cut out so the sides can be folded up to make a box. What dimensions will yield a box of maximum volume? What is the maximum volume? Round to the nearest tenth if necessary. So quickly, what quantity are we trying to optimize? Right here, I saw the word maximum and following it is the word volume. So we want to find the max volume of this box. Okay, great. Then that tells me my goal is to figure out a function representing the volume of this box, and it needs to be a function of one variable. How are we making this box? We have a thin piece of cardboard, 50 inches by 50 inches. So it is a square to start off with. And then we're going to come through and cut little squares out of each of the corners. So this gets cut here, and here. Did you ever do this as a kid? No, I would do this. I would get like little pieces of paper or cardboard cut up. I would make lots of little beds for my dollies, all sorts of stuff. Okay. So imagine the blue shaded parts are gone. They've been removed. And then these pieces here, these sides get folded up. So then this right here, let me show you. This ends up being like the base of the box. It's going to be open top. Yeah. And then these are the four sides of the box. And then you can, in practice, should you care to construct this, you just tape or glue these little sides together, depending what you use to make it. It's very fun. Okay. So how can we figure out the volume of the little box that we're going to create? Well, we know volume is length times width times height when we're talking about three-dimensional rectangular solids. So what is the length? Well, I'll say this is the length, yeah? And then this is the width. And then imagine when the sides get folded up, this is the height right here, yeah? Okay, well, they told us originally the box, or this paper, cardboard that we're cutting up, is 50 by 50. So that's 50 inches. That's 50 inches. That's not how long the length is though, or the width, because we cut into it. And I don't know how much we're cutting into it. It just says that these are square corners. So I'm gonna call this X and this is X, right? These are all X's. All right, then hopefully you can see the length is 50 minus 2X. Whoa, that was bold of me to say. Okay, let's make sure you believe me. This is 50. This much is X. This much is X. So if I cut that out of each side, then what's remaining here for the length is 50 minus 2X. Yes? Oh, good. Similarly, what would the width be? Well, let's see. This is originally 50. We're cutting X and X. So this is also 50 minus 2X. And then the height, this is the height here, and that's just X. So it looks like I'm able to express length, width, and height all in terms of X, which is great. So I have V, volume, as a function of X. It's 50 minus 2X times 50 minus 2X times X. All right, let's see. Job 1 is done. Identify the quantity you want to optimize. It was volume. Express it as a function of one variable. Now it's time to find F prime and critical values, or V prime in this case. So let's multiply it all out before we get going. V of X is going to be, this is just 50 minus 2X quantity squared. So it'll be 2500 minus 200X plus 4X squared times X. And then let's distribute that X and put everything in descending power so it looks better. So we'll have 4X cubed minus 200X squared plus 2500X. So there's our volume function. Lovely. Now time to take a derivative. Okay, so V prime of X, it's just a polynomial, so it should be relaxing. Derivative of 4X cubed is? Good, 12X squared. Derivative of negative 200X squared minus 400X, good, plus 2500. Now, our critical values come from two places, typically. One is where the derivative equals 0, and the other one is where the derivative does not exist. Typically, in optimization problems, this case is not so useful, and it won't apply. And in this case, since look at our derivative, it's just a lovely little polynomial. Well, we know polynomials, their domain is all real numbers. So when it comes to where it doesn't exist, that's not going to happen. This polynomial is everyone's friend. Okay, but I can try to see where it's equal to 0. So that would mean 12X squared minus 400X plus 2500 is 0. Let's see, I can divide everybody by 4, can't I? Then this is 3X squared minus 100X plus 625 is 0. Does that factor? The only way to get 3X squared is 3X and X. Let's try 625 is 25 times 25. Let's hope for the best. So this would be negative 75, negative 25. Perfect. There's my negative 100. Okay. So I get either X is 25 over 3 or X is 25. Whew, what do you do when you have multiple critical values? Well, just compare them. A lot of the time you'll just naturally throw one away because it won't make sense in the domain of the problem. What do I mean by that? Well, say X was 25. This side originally was 50 inches. And since we're cutting out X and X on each side, if X was 25, you'd be cutting 25 here, 25 here, and you would not be having a box left, right? You would just be cutting the whole thing in half. So the length and the width would be 0. So this is not in the domain of the problem. If X equals 25, we would have no box. So I'm throwing that one away. And usually that'll happen if you get more than one. One of them won't make sense in answering the question, okay? Good. So we've got our critical value here. So most likely x equals 25 over 3 is going to give us our max volume, but I do need to confirm, right? You could do first derivative test, like where you make your number line and you check for increasing, decreasing, like you just learned with graphing problems. But usually for optimization, it's nicer just to do the second derivative test. So I'll remind you what that is. We come over here, here's v prime. Now we need v double prime. So v double prime of x would be 24x minus 400, right? Okay, so to verify that x equals 25 thirds yields a max, you substitute that critical value in for x into the second derivative. So v double prime of 25 thirds is 24 times 25 thirds minus 400. And all you're interested in is whether this quantity is positive or negative. So this comes out to negative 200, which is obviously less than 0. So what does that tell me about the concavity of v at that critical value? Well, the graph is concave down at x equals 25 thirds. And I know the derivative was 0 at x equals 25 thirds. So the tangent line, horizontal, right here. Clearly you can see using the second derivative test, it yields a max, so we're good to go. Now that that's taken care of, we can answer the question. So it says what dimensions and then what is the max volume. So the dimensions, remember we said the length was 50 minus 2x, so that's going to be 50 minus 2 times 25 thirds. So that's 50 minus 50 thirds, which is 150 thirds minus 50 thirds, so that's 100 over 3. And the width was the same, and the height we know was just x, which was 25 over 3. So I'll write the dimensions like this. You would say it's 100 over 3 inches by 100 over 3 inches by 25 over 3 inches. That's the dimensions. And then they did also ask for the max volume. So you would just multiply all of these together. So the max volume would be 100 over 3 times 100 over 3 times 25 over 3. So that's 25,000 over 27. Don't forget your inches cubed, right? If it's volume, then the units have to be cubed. Okay, I'm not going to write it as a decimal. My students don't have calculators when they take exams, so if you do, just punch it in and you can round it to a 1 decimal place, but I don't usually mess with that. Okay, very good. Shall we do another? Yes, let's do another. Okay. A company is constructing an open-top, square-based, rectangular metal tank that will have a volume of 33 feet cubed. How precise. What dimensions yield the minimum surface area? Round to the nearest tenth if necessary. So boom, can you see already what we're trying to optimize? Surface area. And we want minimum surface area. Min surface area. Okay, so let's see, what sort of shape are we talking about so I can try to come up with the formula for the surface area. They're telling me it's an open top, square-based rectangular tank. What is this tank for? Little fishes? I don't like that one. It's not cute. This feels better. Great. Okay. Copy. Paste. Lovely, right? Isn't it? Good. So it's an open top, square base. So So I'll call one side x, the other side x. And the height, I don't know. Let's call it y. Why do I call it y instead of h? X and y are usually easier to work with. Also, when you're naming variables in math, if something is like a horizontal distance parallel to x-axis, we call it x. And then when something is vertical, we usually call it y. It's just nice for the brain, right? Okay, be nice to yourself. Can we come up with a formula for the surface area? I think so. Yeah, we should be able to. I'll just call it area, okay? Let's see, how many surfaces are there? Well, there's the base. What's the area of this base? It's just a cute little square, right? So the area is going to be x times x squared. It's open, so we only have one x squared. And then let's see here, the sides. Here's a side. What's the area of that side? It's going to be x times y. X times y. There's one side. Here's another one. This is also x times y. And then this one on the side here is x times y, and the back is also x times y. So we've got 4 xy's. So we have 5 surfaces total. This is the base, and then these are the sides. All right, that looks lovely. Well, we didn't quite do what we need. Whatever quantity you're trying to optimize, you need it to be a function of one variable. And I'm looking over here and I see 2 variables. And right now we're only in calculus 1. So we only do calculus with functions of one variable. This is a no-go. However, is there a piece of information that they gave us we haven't used yet? Read the problem again really quick. Usually they give you some extra info that at first seems random and then will come in clutch right now. Yes, it's that the volume is 33 feet cubed. Okay, you're like, we're trying to minimize surface area. Who cares about volume? Don't worry, that's to help us get rid of extra variables. That's why that's there. So volume is 33 feet cubed. And we just talked about volume in the last problem. So you should be able to come up with an equation for volume of this thing. Volume would be length times width times height. So that would be x times y, which is x squared y. That equals 33. Well, it looks to me like the easiest thing to do with this extra info, solve for y in terms of x and then plug it back in there and we should be fancy free. So y equals 33 over x squared. And then now I can say a is a function of x alone, and it equals x squared plus 4x times 33 over x squared. Whoo, look at us. Okay, let's clean it up because the next thing I'm going to need to do is take a derivative. So a of x is x squared plus 4 times 33 is 132. And then this x is going to cancel with one of the x's here. And I'm going to write it as x to the negative first instead of over x because I know I'm going to need to take a derivative next. So I want to get everything ready. Okay, cool. So let's take a derivative so we can get our critical values. So a prime of x would be 2x minus 132 x to the negative second. All right, so let's go ahead, see if we can find our critical values. I always tell my students, get a common denominator and clean it up. That's more important when you're doing graphing problems, but just to keep good habits, let's do it here. So put the x to the negative second in the bottom, and then I'll get a common denominator, which is x squared. So if I multiply this guy by x squared, now I have 2x cubed minus 132 over x squared. Okay, good. So our critical values happen when the numerator is 0, when a prime of x is 0. So that would mean 2x cubed minus 132 is 0. Can we solve that? You bet. 2x cubed is 132. Divide by 2, that would mean x cubed is 66. So x is cube root of 66. Other place we get critical values is where a prime of x does not exist. So that happens when the denominator of your derivative is 0. That would happen if x is 0, but again, that's not in the domain. Ooh, what's this weird thing I wrote? That means not an element of or doesn't belong to. Okay, it's not in the domain. So think about it. I mean, the problem's funny. It's like, get us a minimum surface area. And you're like, I got it. Don't even make a box. If x is 0, there's your minimum. No, we got to make a box, okay? You can't, imagine if you tried to do that at work. Okay, so check that one out. We only got one critical value. Now I need to verify that that yields a min. So verify x equals cube root of 66 yields the minimum surface area. So in this case, let's go ahead and do the second derivative test again. So I need to compute a double prime. Make sure you don't use this version to get another derivative, because then you'd have to do quotient rule. That doesn't sound fun. I'm going to use this version of the derivative, the first derivative, to take a second derivative, okay? So let's copy this guy down here. That's a prime. So a double prime would be 2. Remember, you bring that exponent down in the front, multiply by it, so it's going to be plus 2 times 132, 264, x to the negative third, which is 2 plus 264 over x cubed. Don't clean it up anymore. All you need to do is plug in your critical value, which is cube root of 66. Whoop. So that equals 2 plus 264 over, well, look, if I'm going to cube a cube root, that cancels. So then I just have 66. And I don't care what number this comes out to. All I'm interested in is if it's positive or negative, right? Which I can already tell it's positive, which means the graph, my area function is concave up at that critical value. That critical value is where the derivative was 0. Right there, there's sweet little cube root of 66, and we can see clearly it yields a min. Great. What else did they want from us, these people? What dimensions? Okay, so they want the dimensions. So we know the base is going to be cube root of 66 by cube root of 66. That's x. I need to know what y is. Well, come right here. So y is 33 divided by x, which is the cube root of 66 squared. Kind of gross. If you're in my class, that's how you're going to leave your answer. Okay, so you would say the dimensions are cube root of 66 feet by cube root of 66 feet by, why did I write the x so high up there? By 33 over cube root of 66 squared feet. That would be the final answer if you're one of my sweet students. Okay, if you're not and your teacher wants you to, punch it in your calculator, then do it. It's approximately, if you round a lot, 4 feet by 4 feet by 2 feet. Okay? Very good. All right, let's try another. I like this one because it looks frightening, but it's not hard. It will weed out those who are weak-minded. Okay. A private shipping company will accept a box for domestic shipment only if the sum of its length and girth, if you don't know what girth is, they're telling you distance around right here. I even like how they wrote distance around here. So good. The sum of its length and girth does not exceed 90 inches. What dimensions will give a box with a square end? Oh, that's important. This is a square, people. The largest possible volume. Ooh, there it is. Largest volume. So we want to maximize volume. That means I need to come up with the formula for the volume of this thing. Okay, again, rectangular solid. They already told me this is a square end, so this is x, right? The length, what should we call it? Not L, people. Do you like taking derivatives and having L's floating around? No, pick something nice and easy like y, x and y. When you get too fancy and weird with your variables, it just makes the problem harder, okay? So don't try to be cute and clever. Just keep it x's and y's whenever possible. Also, don't use d for distance because when we take derivatives, we write d a lot, so call it something else. All right. Can you come up with the formula for volume? Yeah, it's just x times y, right? Length times width times height. However you slice it, it's x squared y. Volume is x squared y. Okay, can we go ahead and take a derivative? No, we cannot, because this is a function of two variables and we need a function of just one variable. So what info have I not used? This lovely piece of info here. The sum of the length and girth of this box can't be more than 90. Oh, so the sum of the length here and the girth, this plus this plus this plus this, can be 90 max. Well, the length is y, and the girth is x plus x plus x plus x, so 4x. It has to be less than or equal to 90, but since I'm trying to maximize volume, I want it the biggest possible, right? I want it to just straight up equal 90. Okay, how is that going to help me? Can I somehow now reduce this guy to only having one variable? Why, yes. Y equals 90 minus 4x. So I can write volume as a function of x now. It's x squared times 90 minus 4x. See that? Oh, that wasn't so bad, right? I'm telling you, 90x squared minus 4x cubed. This is a relaxing little problem, but it just looks intimidating, you know? Get it together. What's the next step? Yes, we take a derivative so we can get our critical values. So v prime of x is going to be 180x minus 12x squared. Whoop. Let's box this. This is good stuff. Okay, so critical values come from two places where v prime of x equals 0 and where v prime of x does not exist. We have a polynomial, so this case is not going to happen. It exists everywhere. The derivative equals 0 if 180x minus 12x squared is 0. I can factor out a 12x from both these guys. 180x divided by 12x would be 15 minus x is 0. So we either get 12x is 0, which means x is 0, or 15 minus x is 0, which means x equals 15. X is 0 makes no sense, right? Then we have no box. So here's our one and only critical value. Now let's verify that it yields a max. So take another derivative. Here's v prime. We need v double prime. So v double prime of x is 180 minus 24x. What do I do now? Plug in the critical value. So v double prime of 15 is 180 minus 24 times 15. So that's 180 minus 360, which is negative. So what does that tell me? The graph, the function for volume is concave down at that critical value. So yes, it yields a max. Woohoo! And they want the dimensions. Okay. So we know x is 15 inches. So, oops, this is 15 inches. This is 15 inches. And so y is going to be 90 minus 4 times 15. That's 90 minus 60, which is 30 inches. So the dimensions are 15 inches by 15 inches by 30 inches. Woohoo! Very good. How are you doing? Are you getting used to that? That would make me happy if you are. Okay, let's try another. A rectangular sheet of perimeter 27 centimeters and dimensions x centimeters by y centimeters is to be rolled into a cylinder as shown in part A of the figure. What values of x and y give the largest volume? Largest volume for this guy. That's what we're trying to optimize. Have you ever done this before? Can you imagine what's going on? You have, pretend like a sheet of paper, and you roll it up into this cylinder, okay? A lot of students like this problem. You know why? Because they already labeled this sucker. So we want to come up with a formula for the volume of this cylinder, and we want to maximize it, right? Because it says largest. So maximize volume. You remember the formula for volume of a cylinder? Area of the base times height. In this case, the base is a circle. So area of the base would be pi r squared. And then the height is y. Nothing is looking good right now because we've got way too much going on. R's and Y's, what in the world? Okay, let's see what we haven't used. Lots of information here. They told me this rectangular sheet, this guy right here, has a perimeter of 27 centimeters. Oh, that means x plus y is 27. So 2x plus 2y is 27. I'll save that. The other important thing is, and they even are trying to help you out here. Look, they feel so sorry for us. The circumference is equal to x. That means all the way around here is equal to x. Yeah, that makes sense because this got rolled into the base, of course. So circumference of a circle, perimeter of a circle we call circumference, is 2 pi r, and that's equal to x. So it looks like I have more information about x. I'm going to try to rewrite both r and y in terms of x. So r is equal to x over 2 pi. And then I could say 2y equals 27 minus 2x. So y is 27 over 2 minus x. And both of those quantities I'm going to sub in now to the volume equation. So I can write volume in terms of x. Ooh, did you see that coming? So volume equals pi times, instead of r, I'm going to write x over 2 pi squared times y, which is 27 over 2 minus x. See how lovely? Okay, now it looks a little frightening, but don't worry, we can clean it up. No big deal. This is going to be pi times x squared over 4 pi squared times 27 over 2 minus x. And since we're going to take a derivative, I want to make it as nice as possible for me to do that. These are just constants, and in fact, I can cancel out one of the pi's, right? Bam, bam. So just put 1 over 4 pi in the front because it's just a constant, okay? 1 over 4 pi. And then I'm going to distribute only the x squared through. So now you have 27 over 2 x squared minus x cubed, okay? Use this version, and excuse me, why didn't I say v of x? Okay, my groceries just got delivered. It distracted me for a second. Okay, we're good. So now we're going to take the derivative. Let's rewrite v of x one more time so you can see clearly. 1 over 4 pi times 27 over 2 x squared minus x cubed. Oof, love it. Okay, derivative time. V prime of x. No, you're not doing the product rule. If you just have a constant, see how there's no variables here, times a function, the constant just comes along for the ride. Just leave him there. Okay, now derivative of 27 over 2x squared. When you bring this 2 down in the front to multiply by it, it's going to cancel with this 2. So then I just have 27x to the first minus 3x squared. Love it. Okay, critical values. V prime of x equals 0. This 1 over 4 pi doesn't do anything. If I set this derivative equal to 0, and then I would divide both sides by 1 over 4 pi, I'd still have 0 equals this lovely stuff in parentheses. So just ignore that constant. 27x minus 3x squared is 0. Factor. You can take out a 3x, and then you have 9 minus x is 0. So either x is 0 or x is 9. This won't work because no cylinder. And then v prime of x does not exist. That doesn't happen. Okay, so here's our one and only critical value. Now remember, we wanted a max volume. So I need to verify that x equals 9 yields the max volume. So let's take another derivative, okay? So v double prime of x, leave the 1 over 4 pi. Derivative of 27x would be 27 minus now 6x, right? So v double prime of 9 is 1 over 4 pi times 27 minus 6 times 9 is 54. So I know that's negative, times 1 over 4 pi, this is less than 0. So yes, that means the volume function is concave down at that critical value of 9, so it yields a max. So we're good. Okay, they wanted, I'm pretty sure, the dimensions, right? Or what values of x and y. So I know x is 9. Okay, so x is 9 centimeters. And then here we know y is 27 minus 2, 27 over 2 minus x, minus 9, which is 18 over 2. So that's 9 over 2. So y is 9 over 2 centimeters. Okay. And for this particular case, you can say what x and y equal instead of just giving like the dimensions without using the variables, because they told you x should be this side, y should be this side. But in all the previous ones, like we picked what x and y represented, so you don't want to give your answer in terms of your special variables. You just want to answer the question that they posed generically, right? Because someone else could have picked x and y or different variables altogether. So don't give your final answer that way, unless they already tell you what every variable should represent. Okay, I still have 1, 2, 3 more examples for you. They're more econ examples, so I'll stop here and then record that separately. And they have just more like, economics applications, which is good stuff. I actually started off as an econ major in college. Long story. Well, first I wanted to major in English, and then it turned into business and then econ. And then I realized I didn't really like econ, but I had taken so much math and I loved the math, so I just double majored for my undergraduate. But anyways, so we'll do some econ later, but the video is going to end right here. Give it a thumbs up if you found it helpful. If you made it to the end, leave me a comment. Be like, I'm a survivor. I'm a trooper. Give it a thumbs up. Yes, please subscribe if you haven't already. And then if you go to the Calculus 1 video lectures playlist, I do have more videos on optimization and stuff like that, and other topics that you might need. You can also follow me on Instagram, TikTok at MathTV with Professor V. I'm going to go unload my groceries and then probably record the other 3 examples. Okay? Have a great one, you guys. Bye-bye.